Let me recall the theorem that I proved last lecture. Where is the chalk? So proved on Tuesday. So we have x over number field k, little x, and set yes, no, set s we don't need. So just as before, and we assume that the condition B holds. That there exists two independent, it means non-proportional, principal divisors supported on the poles of X. Principal divisors over K bar, so they're not obliged to be defined over K bar. Then Ziegel's theorem is effective on the couple capital X, XS, which means that for any finite extension K prime and any S prime finite set S prime, MK prime, the set X of X OS prime is effectively bounded. In terms of X geometric data and K prime S prime arithmetical data. So this is what we proved last lecture, and I wanted to apply this to modular curves. So I introduced all the definitions about modular curves, but I did not state what this theorem gives for modular curves, and it gives basically everything. Yes, so let me recall also definitions about modular curves briefly. Modular curves. So we have for every n number n, every number n such that positive integer, and every g subgroup of GL2 of Z mod n, and we just assume that G contains plus minus 1 to simplify. We denote, so every data like this gives rise to a modular curve xg, as I spoke last time, and this curve xg, well, not really important for this moment. It would become important when we speak on Runge's method, but just now we can notice that it is defined, means has a geometrically reducible model over a certain field K, where K is the field the cyclotomic field, the part of cyclotomic field invariant with respect to the subgroup determinant of G, where determinant is just determinant of G is just determinant of all matrices from G. So in particular, if the determinant of G is full, then this is Q. Now, so we have a curve. Now, what is the coordinate? Of course, a natural kind of coordinate, and the only natural kind of coordinate here is J invariant. And in fact, even one can define using, this sort of neuron models, and so define the notion of integral points, but exactly coincides with the notion of point integral with respect to J invariant. So we'll simply define, and so J invariant is a certain function on xj, and we consider so the question is Ziggy's theorem effective for the tuple xg. Well, of course, provided we have Ziggy's theorem. It can be that we don't have it simply because it's curve of genus 0 and the J invariant has one or two poles. So then in this case, no. But otherwise, so assume that the main assumption of Ziggy's theorem is satisfied and whether it is effective. And it turns out that the answer is very, very nice. It is, well, usually yes, or almost always it is. So this is probably the most impressive example where Baker's method works and produces effective Ziggy's theorem among all that I know, because modular curves are very important, and so having effective Ziggy's theorem for them it's very good. So let me, and everything follows from the following classical theorem from the theory of modular curves, called the theorem of Manin-Drinfeld. I think that it was idea of Lang to call it theorem of Manin-Drinfeld. Again, I'm pretty sure that this was known in this or that way well before, and I will say give some arguments a bit later to support this point of view. But well, it's traditional to call it theorem of Manin-Drinfeld. Let us call it theorem of Manin-Drinfeld. And theorem is very simple. So what are the poles of J? It's exactly the cusps. So theorem tells that basically all divisors of degree 0 on the cusps, well, up to a factor, are principal. So let D divisor of degree 0 supported on the cusps. Then there exists a non-zero integer such that MD is principal. totally fantastic theorem. And in Lenck's book, Introduction to Modular Force Dussault, there is a proof of the theorem, which I personally find, well, it's a nice, elegant proof, which I personally find totally incomprehensible. Not logically. Logically is okay, but I do not understand what goes on there. But, well, and here is the way how I understand this theorem. It simply means that any function, any principal divisor, for any combination of principal divisor, if we take certain multiple, we obtain this divisor of functions. So there are many functions. Supported on the cusps, many rational functions. And it turns out that these functions, in this form, it does not give anything. Well, this principle does not give anything. What the number m, and what we can say about the function for which it is a principal divisor and so. But actually, everything can be done very explicitly. And for applications, it is very important. How it can be done? In the following way. One uses the following object called Siegel functions. So let A1, A2 be a couple of rational numbers, which is not a couple of integers. So at least one of them is non-integral. And we consider the following function, and we call it A. GA of tau I think it is put minus in here. Then we put some term like Q tau. So minus here stands some root of unity. So some exponent of expressed in terms of A1 and A2 that I honestly forget. I forgot to look into the book. I cannot remember it by heart. Some root of unity here, together with minus, some root of unity. And now here we have Q2 to 1/2 of B2 of A1. I will, in the pause, I will probably look and say which root of unity is here. But it doesn't really matter for application. Q tau. And where Q tau is, I will write simply Q. Q or Q tau or Q of tau is just the usual guy. Sorry? And B2 of x is x squared plus x plus, I believe, like this. Good. And here we have a nice product. And I thought that I would remember, but no, it is Yeah. Ah. I think it is like this. It is zeta n. Zeta, no. Well, I will check it. I thought that I will reconstruct by heart, but probably I cannot. So I will check it. I will rewrite this formula. What's important? That's some function which is totally explicit and given by some nice infinite product. So something that we can calculate. And this function has a wonderful property that if A has denominator n, big N, well, again, I have to take away z squared. Then GA to the power 12n is gamma of n automorphic. I think I now remember. I think it is 2e to 2 pi I a2 qn plus a1, and here 1 minus e to 2 pi I minus this qn plus 1 minus a1, something like this. Well, the precise form of this product is important only when you start applying it. For us now, since I argue rather qualitatively than quantitatively, it's important simply that we can write it down. There is something totally explicit. Something absolutely explicit, some absolutely explicit expression. Is gamma of n automorphic? Of weight 0. So it is automorphic function, not an automorphic form or whatever. It's modular function of weight 0, modular function with respect to the group gamma of n. Which means that for gamma in gamma of n, we have GA of gamma tau is equal to GA of tau. Yeah? Sorry, why it converges? Yes, because Q is tau has imaginary part, positive imaginary part, which means that Q is in absolute value strictly smaller than 1, if you put it here. And then, of course, it must converge. And converges quite swiftly. But I would like, well, you see, we do not suffer from the convergence. What usually makes the main trouble are the first few terms. So in particular, for n equal to 0, we have term this q to a1, and here q1 minus a1. And when a1 is very small, say like 1 over n, we obtain something very close to 1. And if there is no root of unity here, we obtain here something very close to 0. And this creates us a lot of technical trouble. And so this is really the most important, the most unpleasant thing about this. But convergence here is very good. Sorry? Well, I think that yes. Well, for n equal 1, simply the set of this function is empty, but everything will have just one cusp, so we cannot have anything. Yes, which means that GA to 12n defines a holomorphic function on the curve x of n. And notice also, so this is first property, And second property, that GA does not vanish as a function on H. Which means that as a function here, it cannot vanish on the finite part. It can vanish only at the cusps. And let me say, holomorphic and does not vanish. As CD just noticed, it always converges. CD, right? Yes. As CD just noticed, it always converges, so it means holomorphic. And also, how can it vanish? Look. Cannot vanish. Each term is non-zero, and they turn to 1, so it cannot be 0, the product. Again, it converges to, yes, so. This is non-zero, so it's never 0. Holomorphic, it does not vanish, which means that this function, GA over 12n, defines what is called a modular unit, a function with zeros and poles on the cusps. Has zeros, yes, viewed as function on x of n, is supported on the cusps. And so it gives us some principal divisor. It gives us some principal divisor with support on the cusps. And now some argument, you can find it, for instance, in the infamous book of Kubert and Lenk, Modular Units, proves that these divisors form a maximal possible, generate an abelian group of maximal possible rank equal to number of cusps minus 1. And this implies, of course, the theorem of Manin-Drinfeld. So it gives a constructive, a purely constructive proof of the theorem of Manin-Drinfeld, these functions, supported on the cusps. And the theorem, I don't know, but I believe that certainly Siegel already knew it. So that, so let us call this function in certain way. So let us call the function UA. Good? So the principal divisors UA generate abelian group of rank nu infinity of n minus 1, where nu infinity of n number of cusps on x of n. The proof is, well, just proof. Yes, and this implies the Manin-Drinfeld theorem for x of n. And for xj, that is just immediate. If we have on x of n sufficiently many functions, then from them taking suitable norms or so, we can also find sufficiently many principal divisors on cusps of xj. Manin-Drinfeld theorem on xj. So I'm not going to prove this because the proof, well, I used this theorem last 5 years or so, and I never bothered to read the proof, which means that probably the proof is not very useful for applying the theorem. So you can easily use it as, well, it's probably not that I once I read, but then I forgot. So it does not teach you anything important, but it's just a statement that tells you something. But you find that it is proved in a suitable place in Kubert-Leng book. So you may find it there. And what it means that we can do everything very, very explicitly. Particularly, we can obtain, not only prove theoretical that Ziegel's theorem is effective on a modular curve, but we can do it, we can get very explicit bounds. Now, let me state how it looks, Ziegel's theorem on modular curves. So an immediate consequence of the theorem of Manin-Drinfeld and this main theorem is that if we have at least 3 cusps, then Ziegel's theorem is effective. Because in this case, we already have 2 independent divisors. So I call it 3-cusp criteria. If xg has at least 3 cusps, then Ziegel's theorem is effective for the couple xg j. And a purely explicit version of the theorem using exactly the construction of Ziegel functions. So it was made in my article some around 95 or so as just one of observations, but I never made it explicit. In particular, that at that time I did not know about existence of Ziegel functions. But recently it was made totally explicit by my PhD student Xiamin. Please remember this name, you will probably hear it again. So this was around 1995, published. So Xiamin obtained a totally explicit version of this result. And also with Aurélien Bajolet, my another PhD student, they obtained a very explicit and very sharp version on the special case, interesting special case, Xiamin and Aurélien Bajolet, another PhD student of mine, obtained very sharp for xg equal to the curve associated to the normalizer of non-split Cartan subgroup of level P and over Z. And only. So only for Z points with Q. Rational with integral J invariant. So this was both around, so I think that this is around 2012, this is around 2011, so. Good. Now let us see what it gives for interesting curves. Well, here, of course, P must be, as we shall see in a while, P must be greater or equal to 7. Otherwise, simply Ziegel's theorem doesn't hold. Curve and mu infinity number of cusps. So if we take x of n, first of all, the principal modular curve, then the number of cusps is what? Is 3 when n equals to 2, and 1/2 n squared product p divides n 1, and always greater or equal 3 when n is bigger than 2. So we have, in all cases, at least 3 cusps, except the trivial case n equal to 1, so it holds. Now, probably the most interesting modular curve, x0 of n, the number of cusps is this one, sum the GCD of d n over d, where the sum is over the divisors of n. And this is greater or equal 3 exactly when n is composite. So it gives effective Ziggy's theorem for x0 over of a composite level. And if we take prime levels, then x split plus of p has p plus 1 over 2 cusps, and x non-split plus of p has p minus 1 over 2 cusps, so it is at least 3 for p, at least 5. This is at least 3 for p, at least 7, and so again we have effective Ziggy's theorem for these curves. Well, and many other. Interesting case which remains not covered is x0 of prime level. So for x0 of prime level, we have only 2 cusps. But it's 2 cusps, so this theorem does not apply. So 3 cusp criterion does not apply. But it's not difficult to show that it admits a tal outside the cusps morphism covering, let us say, by a curve with at least 3 cusps. And so, adding to this Chevalier-Weil principle, we obtain that also Ziggy's theorem is effective for x0 of p. And again, Chamin obtained some bound, but this time the bound, well, I don't like the bound he obtains. It is not really. I think that one can do much better than what he does. So I invite to do it better. And in general, well, one seldom meets modular curves with few cusps. And one can even give more or less complete description of all modular curves with two cusps. And for many of them, with one or two cusps, and for many of them, well, either Ziegel's theorem does not apply, they are genus 0, then we forget. Or if it applies, sometimes we can also, again, argue like this, find some covering. And going into this direction with my PhD student, Marco Elengo, again, I always forget here. I think it was something like 2010. Proved that Ziegel's theorem is effective for almost all, in the sense all but finitely many, couples, all xj. So, which means what almost? Means that simply we prove the theorem. If level, I mean the exact level. So each, of course, if we have a curve, we can make it on level n, then we can make it in any other level, in any higher level, in any level divisible by n. So let's take the smallest level and call it the exact level. And so we showed that if exact level does not divide certain number, then whatever g is, we have at least 3 cusps or whatever, and then we have effective Ziegel's theorem. Yeah. So, sorry? Yes, it is written. It's some big numbers, so we would like to make a more precise result. But anyway, well, in particular, if we speak on prime power levels, at all prime levels and all prime power levels, distinct from 25. Somehow on level 25, we have a curve which is of genus 2 and has 2 cusps, and we cannot do anything. So our approach just breaks down. I think it is actually somehow related to X non-split, maybe some quotient of these curves, but on level not P, but not 5, but 25. So. Yes. And also there are some mixed levels, so levels divisible by several primes. The smallest is 35. Also on level 35, we have again some curve of genus 2, and we cannot do anything. So there are some nasty curves, but there are only finitely many of them. For all the rest, Ziegel's theorem is effective. Good. Okay. This is all what I wanted to say on how Baker's method applies to modular curve. Now I will start the last, say, paragraph or section or whatever of my course, Runge's method. I will introduce first general Runge's method, and then again I will speak on applications to modular curves. So this is done. Now Runge's method. Maybe we can make now a little break, but probably let me say a few words on Runge's method. So let me start some introductory example, and then we'll make a break after the example. Good, will be better. So, what is Runge's method? It is a very elementary. So Baker's method is elementary, but it uses Baker's inequality, which is highly non-elementary. So it is elementary modulo the Baker's inequality. Runge's method is elementary without any modulo. It is just, it uses nothing deeper than the main theorem of number theory that I mentioned in my first lecture. So nothing beyond this. So it is totally, it looks like totally trivial. Nevertheless, it works. When it works remarkably. It is quite ancient. Originates from the work of Runge in the 60s years or so of 19th century. Around, well, I don't remember well, so 19th century. And this is the same Runge whom we know from numerical methods in differential equations, from numerical analysis, Runge-Kuta. So this is the same Runge. And let me give first what I call a baby example. Let me start from a baby example. This is an easy, you can give it, for instance, to high school students as a rather simple mathematical Olympiad problem. So let us consider the Diophantine equation. Y squared, well, equal to x fourth. Well, then I will just write all prime numbers. So x cubed plus 3x squared plus 5x plus 7. Which telling that example is quite arbitrary. But there is something which is not arbitrary in this example. And well, I will say not arbitrary is the coefficient here. Everything would work if this coefficient is a square. If, say, for instance, I put here 2, it will break down there. We want to solve this equation. How we do it? Of course, it's sufficient to find only solutions with positive y. And if we have a solution with positive y, so basically with any y, the solution is given by what? By its plus minus to what? X. Let me take square root of this guy. It will be x squared. And so we want to solve in integers, of course. Sufficient to assume that x is an integer and y is rational. So we again have a set of points, rational and integral with respect to coordinate x. So plus minus x squared, and then we have what? 1 plus 2 over x plus 3 over x squared plus some negligible term, 1/2. And now if we do the exercise, this is just use the binomial formula, what we teach our first year students in the calculus courses, we will find that this, so let me forget about, so again, okay, let me not forget it. So plus minus 1, and then we have x squared plus x plus 1, unless I made a mistake, plus some guy. And now, so if y is positive, then we have obviously plus, and y negative, minus. And now, if say y, then the number y minus this guy is small. But it is also an integer. And so, which means that when x is bigger than something such that this is smaller than 1, now the main theorem of number theory tells us The main theorem of number theory tells us that y is equal to x squared plus x plus 1. And we can easily now see. So we obtain one more relation. So we can just substitute x squared plus x plus 1 here, and we obtain that x is the root of certain polynomial. Which implies that x is bounded by certain C2. Actually, one can even check that there are no roots for this polynomial. So we have, but if we don't want to bother about the roots, we obtain that x is bounded, and we obtain that the equation has finitely many solutions. Actually, I believe there are no solutions, but of course, this can all made be totally explicit. One can calculate it until the end. So this is a baby example, but already this example has everything what Runge's method has in it. And well, let me now state the theorem of Runge. First over Z, and then an arbitrary context. So assume first that so assume that X is curve over Q, and have a coordinate little x, non-constant again, and assume that we have the following condition, that I denote now R. This is for Runge. So we have poles. This function has poles. As a set, poles are defined over Q. But each singular pole is defined over some higher field. And so, of course, we have, if we have one pole, then all conjugates of these poles again. So Galois group, absolute Galois group acts on the set of poles. And assume that this action is non-transitive, that we have at least two Galois orbits of poles. Assume that action, the Galois action is non-transitive on the poles. So each time the condition tells something about the poles, you see. Is not transitive. Then the set of is finite and effectively bounded. And I must say, when both, so formally it is possible that Runge's method applies Baker knot or Baker applies Runge knot. When both apply, usually the bound obtained by Runge's method is much sharper. So when it applies, it is remarkable. Because, well, we don't use Baker's inequality is weak. And when we have to use, we obtain a bound which is quite weak. Runge's Runge's method is just totally elementary. We don't use anything. So we obtain quite a good bound. How it is proved? Proof is very quick. We write poles of X as the union disjoint union. So, and each sigma I as a set defined over Q as a set. So they are non-empty, so we have a partition into two sets. So this follows from condition. Now assume that we have a P in X with a X of P large or big. Big means, again, that P is close to a pole. So there is a pole. Which may not be defined over Q, but it is defined over some extension. And we just somehow extend the infinite absolute value to Q bar, and then there is a pole such that rho infinity, where infinity means that we use here infinite absolute value of Q and P, is small, smaller than X of P to some power minus epsilon, where epsilon is some positive number depending only on the, which is well, constant. Here also involved some constant. And this Q belongs either here or here. So for instance, assume that it belongs to sigma 1. Then we consider what is called Runge function. Notice it's important. This function is over Q. Q of. And it has the following property. Poles of Z are in sigma 2, and zeros of Z contain sigma 1. Well, and if it belongs to sigma 2, we just take another Runge function. So in this case, we need two functions to use. Of course, such a function can be easily constructed using Riemann-Roch theorem, whatever. Now let us see, what this means what? This implies that Z is integral over Q of X. And may assume by just multiplying by some guy, may assume it integral over Z of X. Which means that Z of P is an integer. But this condition means that Z of P is small. It's bounded by the distance, because Q is one of the zeros. To some power. And so it is bounded by and this means that if X of P is bigger than certain number C1, then Z of P is strictly smaller than 1. And by the main theorem of, you see, this is the only non-trivial thing that we use, main theorem of number theory, right? The main theorem of number theory implies that Z of P is 0. So P is one of zeros of a concrete explicitly given function, which again implies that the height of P with respect to whatever is bounded, in particular, the height of P with respect to X, so in which case X is integer. So X of P is again bounded by some other constant, C2. C1 and C2 depend only on the curve and the coordinate X. And we're done. And in the baby example, there are just two poles. One corresponds to the positive sign. The other corresponds to the negative sign. And if, for instance, if we're in the positive pole, then Z is exactly this guy in the baby example. OK, now we'll discuss after the pause. We'll discuss this proof. I will make some remarks. Sorry? Yes, we need non-transitivity to get the partition. Yes. If it is transitive, we cannot partition it like this. We have only one set. The other would be empty. Good.